Previously in Chapter 18, I've gone over schematic diagrams and circuits, and resistors in series and parallel. Now I'm moving on to the final video for this chapter, which is complex resistor combinations. In most circuits in real life, components are arranged in a combination of parallel and series. You rarely find a circuit that's exclusively parallel or exclusively series. So in this video, I'm going to mostly do practice problems, where I'll go over several situations to show how to calculate current and resistance in these complex circuits. So here's the first example. We have this circuit, as I've drawn, that sort of has resistors set up in a combination of series and parallel, and we want to find the equivalent resistance and the current in this series. So to solve for equivalent resistance in this series, we can use our shortcut, where equivalent resistance equals R1, R2, divided by R1 plus R2. And this will help us to solve for resistance just in this little square over here, where the elements are connected in parallel. So we're looking for Req, or equivalent resistance. R1 we'll say is a 30 ohm resistor, R2 is 20 ohms, and then we're dividing by 30 plus 20. This simplifies to 600 divided by 50, or 12 ohms of equivalent resistance. To find the current in this circuit, we'll use V equals IR. We know that the voltage for the battery is 6 volts, so 6 will equal I, which is the current, times 12. We divide both sides by 12, isolating I, to solve for current, which will come out to 0.5 amps. Here's a second circuit with a combination of series and parallel elements. Here, once again, we're finding equivalent resistance and current. So in the last problem, we had a very similar setup, and we found that the equivalent resistance of this part wired in parallel was 12 ohms. In series, we know that the equivalent resistance is the sum of the resistance of each component. So we can effectively treat this parallel part as one resistor, or one component, and then we have a new 10 ohm resistor up top. So the equivalent resistance will equal 10 ohms plus 12 ohms, or 22 ohms. Next, we're solving for current, so we know that V equals IR. V in this case is 6 because it's 6 volts again, so 6 will equal current times the equivalent resistance, which is 22 ohms. If I divide both sides by 22, I get that the current equals 0.27 amps. In this third situation, I have a circuit that's wired in parallel, and I'm looking for equivalent resistance, overall current, and the current in the 6 ohm resistor. So we're starting with equivalent resistance, and we know again that 1 over equivalent resistance will equal 1 over R1 plus 1 over R2, etc. We're going to solve for equivalent resistance. And we're not going to use our shortcut in this situation because there are more than 2 resistors. So we'll do it the old-fashioned way, where this is equal to 1 over 6 plus 1 over 3 plus 1 over 2, or 1/6 plus 2/6 plus 3/6. We get that this all comes out to 1. So equivalent resistance in this parallel circuit is 1 ohm. The second part is overall current. So for the sake of this, we can essentially treat all 3 resistors as one resistor with a strength of 1 ohms. So if V equals IR, and we know that it's 12 volts, 12 equals I times 1. We divide both sides by 1 to find that I, or the current, is 12 amps overall. Finally, we're looking for the current in the 6 ohm resistor. So here we're treating it almost like a series, with only the path through the 6 ohm resistor. Again, we'll use V equals IR. The V is 12, the current is what we're solving for, and R is 6. Divide both sides by 6, and the current is 2 amps. Here's a final example with a combination of series and parallel elements. Here we're looking for the equivalent resistance and the current in the 4 ohm and 6 ohm resistors. So to find the equivalent resistance, we'll start just with this part where the bulbs are wired in series. So we have 8 plus 4, which would be 12 ohms, or equivalent resistance, because you simply add them in a situation with a series. Now it becomes similar to a parallel circuit, where equivalent resistance, here we're using the shortcut, is equal to R1 times R2 over R1 plus R2. So we'll plug in the values we already know. We'll call R1 6 ohms, R2 is 12 ohms because that's this entire segment, and that's divided by 6 plus 12. So we end up with 72 divided by 18, or 4 ohms. That's the equivalent resistance for the entire circuit. Now we want the current in the 4 ohm segment. So we'll use our equation V equals IR. We can rearrange the equation because we're solving for current, so we'll divide by a resistance to find that the current will be equal to V divided by R. Now we plug in the value of the battery, which is 6 volts, and we'll use the resistance across this entire segment of the circuit, so 4 plus 8, which is 12. 6 divided by 12, we get that the current is 0.5 amps. For the current in the 6 ohm portion, we'll use the same equation, V equals IR, or I equals V over R. Plug in the new values, and I is equal to 6 over 6, or 1 amp. This has been Chapter 18 of Holt Physics. We've looked at schematic diagrams and circuits, gone over resistors in series or in parallel, and explained complex resistor combinations. Thank you for watching.